Here we are for Honors Physics, Worksheet 5, Friction. Okay, and we're going to go ahead and skip right to problem 6. Problem 6 this has the sketch. It says a 2-kilogram block is slid across the floor of an elevator while the elevator is accelerating up at 3.2 meters per second squared. If the coefficient of kinetic friction between the block and the floor of the elevator is 0.7, and the block begins sliding at 5 meters per second towards the wall, which is 1.5 meters away, will the block make it all the way to the wall? If so, how quickly will it be moving when it hits the wall? If not, how far away will it be from the wall when it stops? So I'm going to go ahead and discuss this problem on the piece of paper, give myself plenty of space. Okay, so I've got plenty of room here. All right. So first thing is, I'm going to go ahead and they already gave me a sketch. I'm going to go ahead and jot it down again, though, because I'm just that way. Because I'd like to have everything on one sheet of paper here. So if I go ahead and do that, let's see. I've got my elevator. Okay. And while the elevator compartment, okay, there is going to be accelerating up at 3.2 meters per second squared. We have that block inside that's starting off moving at 5 meters per second. All right. And we know that the distance between it and the wall there is 1.5 meters. Let's see. So the question is, given that the coefficient of friction with the floor is 0.7, is this going to make it all the way to the wall? If it does, how fast is it going? If it doesn't make it all the way, where does it stop? So running through this, you say, okay, my system, of course, I'm going to pick just the block. Okay. And so I'm going to go ahead and do a force diagram just because I know it's going to be useful. So let me go ahead and sketch that here. There is that little block. And we'll say force is acting on it. So running through my list sequence of questions, I always ask, first I ask what ranged forces are acting. You'll say there's a gravitational force, mg, from the center of the box to the center of the earth. Then you say, you list everything that's touching the system next, so you can do contact forces. Well, the only thing touching this block while it's sliding along, which is what we're analyzing, how far it goes as it slides along and how fast it's going. You say the only thing touching it while it slides along is the floor of the elevator. It's true that something had to get it started, but we don't know anything about that, and it's not still pushing it. No. It gave it that 5 meters per second to start with, and now it's just kind of sliding along the floor. So I don't need to worry about that. The only thing touching is the floor of the elevator. So now I run through my questions and I say, are those surfaces, the block and the floor of the elevator, being pressed together? And you say, sure. The gravitational force is pressing it into the bottom of the elevator. Plus, we know the system is accelerating up. That floor of the elevator is going to be pushing up to accelerate that block upward. There's going to be a really big normal force there, okay, on the block from the floor of the elevator. Once you have a normal force, the next question we always ask is, are those surfaces trying to slide past each other? And you say, yeah, sure. We know this is sliding along to the right, so there'll be a friction force to oppose that slide to the left, okay, that kinetic friction. All right. And that's the only thing touching the block. There's no ropes or strings or wires on the block here to pull. So there's no tensions. We're done. That's the whole force diagram for this problem. All right. Let's see. We want to go ahead. And since we realize that if it does make it to the wall, we're supposed to calculate the final velocity. And if it doesn't, we're supposed to figure out like where it ends up, like solve for displacement. You're like, we're going to need to do kinematics here. So I'm going to kind of set up my kinematics. I'm going to go to do a motion problem. Now there's actually two different possibilities here, and we're not sure which one happens. Either it makes it to the wall or it stops before it gets there. So I'm going to have to kind of set up for two calculations. If the block reaches the wall, right? And then we'll set up for a calculation for if the block doesn't reach the wall. All right. Now, when I do a motion calculation, I like to list out my 5 motion variables. They'll look like this: A, V naught, V, displacement, and time. Bum, 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 bum. All right, do the same thing over here. A, V naught, V, displacement, and time. That's the way I set up a motion problem. All right, now we're going to fill in what we know. You say, okay, for this one, if it makes it all the way to the wall, we are trying to find the speed that it ends at when it gets there. All right, if it makes it all the way to the wall, we'll know that it has traveled 1.5 meters for its displacement. And we know the starting velocity was 5 meters per second. They told us that. But that's all we know. I know that when I do a calculation in kinematics, there's always 4 variables in each kinematics equation. I need to know 3 values to solve for a 4th. You're saying, I really need a 3rd value. And you say, well, I'm not going to be able to substitute from here because these are 2 completely different situations we're analyzing here. I can't take data from here to plug into there. It's not going to work. So I'm going to have to get acceleration from F equals ma. That's where I'm going to be able to pull that acceleration in and solve. All right. What if we make this assumption that it doesn't reach the wall? Again, we know the starting velocity is 5 meters per second. What they want us to find if it doesn't make it there, they want to know how far, if it stops here, they want to know how far away from the wall it stops. So we're trying to find that displacement. That displacement of the block is going to be this. And then we'll have to subtract it from that 1.5 to see how far away from the wall it is. Now, if it doesn't reach the wall, that means it's going to stop short of the wall, right? So the final velocity would be 0 then. All right, and that's all I know. Again, I only have 2 variables, and I need to have 3 to find a 4th. So I'm going to need to find acceleration. Again, we're going to do that through F equals ma. So we're going to go to our force equations. Now, you'll notice that we called the starting velocity +5, and displacement +1.5, and so on. We have already kind of chosen to call to the right the positive direction, haven't we? So my coordinate axes that I'm going to be using in this problem going to be like this. X and Y. Positive will be up and to the right. All right, and that way this acceleration up is positive as well. So here we go. Let's go to our sigma F equations. I'm going to get my equations from the force diagram. We're going to do for each axis. So we can do it for the horizontal axis. Sum of the forces in the horizontal axis is mass times acceleration in the horizontal axis. And we can write it for the vertical axis. The sum of all the forces, add up all the forces in the y-axis, they should equal mass times the acceleration in the y-axis. All right. Now, an important point I'm going to make just right off the bat here is this acceleration that we want to plug in here. That's the horizontal acceleration, right? This 3.2 they gave us, that's the vertical acceleration. That one we know is 3.2 meters per second squared. But that's not the one we need here because this is for analyzing the sideways motion. We need this. Once we have this acceleration, we're going to be able to go ahead and substitute it in there or in there, right? To do these calculations and figure out which one of these occurs, all right? So first we got to find the acceleration. Here we go. Let's write our equations finally. If I talk about the horizontal axis, we're calling to the right positives, be forces right minus forces left. That's just going to be friction going to the left. So minus that kinetic friction is mass times acceleration in the x. You say, now we're trying to find this acceleration in the x. We do know the mass. They told us it's a 2 kilogram block. We don't know the friction force. They told us the coefficient of friction, though. So I can use my kinetic friction formula. that that friction force is mu times the normal force, that coefficient of friction times the normal force. So I can be substituting in there. That kinetic friction is mu n. Kind of jumping ahead here, that's all right. You say, okay, well, I got rid of one variable I didn't know, but I introduced another one I don't know. I don't know the normal force. You say, well, that normal force, that's going to be one of the forces in the vertical axis, so I need to go to this equation. So we'll do forces up minus forces down, n minus mg, and this does not equal 0 because we are accelerating up and down. So it'll be the mass times that acceleration in the vertical axis, ay. All right, now I do know ay, I know g, I know the two masses. I could solve for that normal force. All right, may plus mg, just adding mg to both sides. And like I said, I could plug in values and solve for n if I wanted to, but for my own purposes here, I'm going to go ahead and choose not to yet. I'm going to go ahead and substitute this in for the normal force there. If I do that, this is going to look like this. Negative mu, and then instead of the normal force, I'm going to have this substituted expression, may plus mg. All right, is mass times my acceleration in the x-axis. Now look, can you see that I'm going to distribute this mu, right? It's negative mu, but you'll see that every term has mass in it, right? And so that means that those masses will just drop right out of the calculation, right? Divide through by m, and bam, 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 those m's go away. So now I'm left with just an equation for the acceleration, the thing I'm trying to find. So you say, okay, let's go ahead and put our values in. So I'm going to have minus mu is 0.7 times acceleration in the y plus g will equal that acceleration in the x. Okay, I can go ahead, punch that in my calculator. 0.7 times the quantity 3.2 plus 9.8, right? And you say, hey, that's going to give me a value of negative 9.1. And that's my acceleration in the x-axis. This is the acceleration. I'm going to substitute in up here now. Negative 9.1. Negative 9.1. Now I know what I need to know to do some kinematics, okay, and figure out which one of these works. Let's try this green one first. Let's see how fast it's going. If it gets to the wall, how fast will it be going? So you say, which kinematics formula do I want? I want to use the motion formula that doesn't have time in it. Remember, I've got 3 different motion formulas. V is at plus v naught. Delta x is v naught t plus 1/2 at squared. And v squared is v naught squared plus 2a delta x. You say the only one of those that doesn't have time, that has these other 4 variables, is the third one. So we're going to go ahead and use that. V squared is v naught squared plus 2a times the displacement. And you say, now, conveniently, v is the variable I'm trying to find. It's already shoved over there by itself. Let's go ahead and just plug in values first and see what happens. My initial velocity is 5 plus 2 times, now my acceleration, this is the horizontal acceleration we just solved for, that negative 9.1. And then displacement, hey, this is assuming it made it all the way to the wall, so that's 1.5. Okay, plug that in my calculator carefully. 25 minus 2 times 9.1 times 5, 1.5. And you say that gives me negative 2.3. So you have that v squared is negative 2.3, and you're like, uh-oh. You're like, I can't have, in order to have something square and be a negative number, it'd have to be an imaginary number. What is this trying to tell you? You say, I'm going to get the square root of a negative. You say, this means it never makes it 1.5 meters. Okay, this is not going to reach the wall. All right, because I'm going to get an imaginary value when I take that square root, right? If I take the square root of both sides, you're like, uh-oh, square root of a negative. So the block doesn't, this never happens. It never makes it that 1.5 meters, is what that's trying to tell you. The block doesn't reach the wall. All right, so we got to go and do this calculation for if it doesn't reach the wall. Okay, hey, look, it's the same 4 variables we had here. So I'm going to use that same formula. V squared is V naught squared plus 2a delta x. This time we're trying to find the displacement. So let me rearrange this. That displacement is going to be the final velocity minus the initial velocity divided by 2 times the acceleration. Go ahead and convince yourself that that rearranges to be that way. We can go ahead and substitute our values in now. Final velocity is what we are trying, is 0 because we're going to stop. That's right, we're not going to reach the wall. Minus the initial velocity of 5 squared divided by 2 times that acceleration we found down here, negative 9.1. And if I punch that in my calculator, 25 divided by 18.2, I get a value of 1.37 meters, rounding that off there. So it's going to slide 1.37 meters before it stops. Okay, now be careful. This is not the value they asked for. They wanted to know how far from the wall will it be when it stops. So the wall is 1.5 meters. It slides 1.37 meters. How far away from the wall is it? You're like, okay. That's going to be 1.5 minus 1.37. You see that's going to be 0.13 meters away from the wall. And that is the answer. Okay, so if I had to point out what I think was particularly tricky in this problem, a couple things. One, you want to do a kinematics, but you realize you don't have enough information. There's 2 possibilities you have to check to see what the right answer is. The fact that there's also acceleration happening in both axes, all right? You've got a separate acceleration for the horizontal and for the vertical axis. That means this normal force and gravitational are not going to balance out. This normal had better be bigger than the gravitational if we're going to accelerate up. All right, so it's just a new situation you didn't have to deal with before. Because that normal force is extra big, that means that friction force, mu times the n, is going to be extra big, right? Which is why it doesn't reach the wall. I bet if this elevator was sitting still, I bet it would reach the wall. All right. Hey, that's it for problem 6.